Hello students, welcome to lecture 14. In the last lecture I discussed about how to solve Schrodinger equation for hydrogen atom. I discussed how to separate between the motion due to center of mass and motion of electron relative to center of mass. We separated Schrodinger equation into two different parts based on small r and capital R, and then I went ahead and showed you how to solve the Schrodinger equation which deals with the motion of electrons relative to center of mass. We are concerned about motion of electrons, and that is why I only discussed the motion of electron and we solved the Schrodinger equation corresponding to the motion of electron. I will again start where I left. In the last lecture, I showed you when you solve this Schrodinger equation, you will get different value of the radial function. The value of radial function will depend on L value. If L is equal to 0, then I showed you what are the different solutions of the acceptable wave function. For L is equal to 1, again I showed you how to get the radial wave function. So, this is the solution which we obtained when we started with L is equal to 0. This was the first solution. We can also get different solution for the same differential equation, and one of them is this. I also told you that the first solution corresponds to your n is equal to 1, whereas next solution belongs to n is equal to 2. So, this is basically wave function associated with the ground state, whereas this one is the wave function associated with your n is equal to 2. So, this one is solution for n is equal to 1 and this is the solution for n is equal to 2. Then I went ahead and showed you what will be the differential equation for L is equal to 1 and what will be the solution. I only discussed one of the solution and that was given here, and we can get your this radial wave function R by using this equation which we assumed before solving the Schrodinger equation. And so, first solution will be simply exponential minus gamma R, this R cancels out. The second solution is simply 1 minus R gamma exponential minus gamma R, and this is the second solution for L is equal to 0 and this corresponds to n is equal to 2. For L is equal to 1, I showed you that if we start with u r is equal to r square gamma exponential minus gamma r, then we will be able to get the answer. One thing you will notice is all these solutions has exponential minus gamma r in common. So, what now we will try to write this is in terms of a general equation which can tell you about the solution of equation. So, one general equation for the solution, and since the solution depends on L value and so L value and n value, so your the general solution will have terms corresponding to n and L. So, let us see what is the solution. The solution is given here. Okay. This is quite big term, but this is the solution, and I will show you how to get the solution for L is equal to 0 or L is equal to 1 from this. So, it is simply minus sign 2 by n a naught q, this is n minus L minus 1 factorial divided by 2 n multiplied by n plus L factorial and cube of that, and then take a square root of the whole term. And then this is your another function of r, and this is the exponential term, and then there is another function of r. In short, what we can do is 2 r by n a naught, let us take this as a rho, and then you can simply write rho by L, and here you can write in place of r n by a naught rho by 2, because you remember rho is 2 r divided by 2 n a naught, and so r divided by n a naught will be equal to rho by 2, and this is again rho. And this is basically known as normalization factor, which certainly depends on n and L, and that is what is written here. So, this is normalization factor rho L e minus rho by 2, and this is your one polynomial. Okay. So, now I will discuss about this polynomial. This polynomial is called Laguerre polynomial. Laguerre polynomial. So, this is basically your this thing. So, L, and at superscript this is P, and here subscript is Q. And if you go back, you can see superscript P is equal to 2L plus 1, and subscript Q is equal to n plus L. So, keep that thing in mind. So, this is your n plus L. Let us go back. This is your 2L plus 1. This is your 2L plus 1. Okay. And this is basically differential with respect to x, and there is a power of p, and then this LQX, this is another function. What is this LQX is your Ex multiplied by d by dx, and you can see that this is power q, this is power q, and E minus x into x by q. Now, it looks quite complicated. It is complicated, but if you try to understand, then it will not be that difficult. For example, first what I am going to calculate is this quantity. If q is equal to 1, so this I took q is equal to 1. What does that mean? Is n plus L is equal to 1. And if I solve this, this is exponential Ex, and then since q is 1, you will write simply d by dx E minus x and x power 1, and that is what is your L1 x. Now, let us solve this. L1 x is equal to Ex d by dx E minus x into x. So, let us first take x constant and then differentiate exponential minus x, you will get minus exponential minus x, and then you take this constant and differentiate x. So, you will get plus E minus x, and since this is multiplied by Ex, so Ex into E minus x is 1. So, what you will get is simply 1 minus x, simply 1 minus x or minus x plus 1. Now, we solved LQX, now we will solve this the second one. So, that is written as L in the superscript you have 1, in the subscript you have 1, L 1 1. Okay. So, this will be equal to d by dx, as since p is 1, and so you have simply d by dx and L 1 x, which we just calculated, and that is equal to minus x plus 1. So, if I differentiate this, what I am going to get is minus 1. So, L 1 1 x is equal to minus 1. So, this is your first polynomial, a value of first polynomial. So, let us go and see for the second one. Again same equation I have written here, so that you should not get confused. And now, what I am going to do is, I am going to take q is equal to 2, q is equal to 2. When we do that, this will be equal to E x d2 by dx square exponential minus x into x square. Now, let us differentiate this. If I do for first time, what I will get is minus e minus x into x square plus 2 x e minus x. In the first term, I have taken x square as constant, and in the second term I have taken e minus x as constant, and so I get this whole equation. Now, L 2 x, this L 2 x still has 1 d by dx term, 1 d by dx term. So, this is E x from here, this point E x. Now, I am differentiating first this term. Okay. Here first I took x square as constant, and then I differentiated exponential minus x. What I will get is plus E x into x square. And now, what I did is I took e minus x as constant and differentiated x square. So, I will get this one. Now, come and differentiate this 2 x exponential minus x. So, what you are going to get is minus 2 x e minus x when you differentiate e minus x, and 2 e minus x when you differentiate x, keeping e minus x constant. And if you see here, these two terms are same. So, you get 4 x exponential minus x. So, this is your L 2 x, and if I simplify this, so E x multiplied by e minus x is 1. So, you are left with x square and minus 4 x plus 2. So, this is L 2 x. So, L 2 x is equal to x square minus 4 x plus 2. So, what we got is this term. Now, I want to solve this one, L p q. So, here p is taken as 1. So, suppose p is 1. So, then what you need to do? You need to differentiate this L 2 x with respect to x. Okay. So, d by dx L 2 x is basically L 1 2 x, and just we solve this. L 2 x is x square minus 4 x plus 2, and if I differentiate this, what I am going to get is 2 x minus 4. So, L 1 2 is equal to 2 x minus 4. Similarly, we can calculate L 3 x. L 3 x is E x d 3 by dx 3 exponential minus x x 3. Remember this thing. So, this is q, q is equal to 3, and so we put it here, we put it here, and then we put it here. And now, first differential will give this term, the second differential will give you this term, and third differential will give you this term. Okay. You can do it, it is simple. This is basically differential of u into v type of differential. So, this differential is of the type of u and u into v. So, when you do that, you will get this term, and finally, what you are going to get is this whole term. And if we take e minus x out, then you will get this term, and finally, L 3 x is this. So, L 3 x is minus x q plus nx square minus 18x plus 6. This is simple differential, a bit lengthy, but it is easy to do. So, once I know L3x, it is very easy to calculate L13x or L23x. So, we will see that. So, L13x should be equal to d by dx, this L3x. In the last page, what we saw is that L3x is equal to minus x cube plus 9x square minus 18x plus 6. So, simply do the differential, what you will get is minus 3x square plus 18x minus 18, and this is L13. We can also get L23. For that, I have to differentiate it again. When I differentiate it again, I will get minus 3 into 2x, that is minus 6x and 18 from this, and you can also get L3x, which is minus 6. So, although it looks complicated, it is not that complicated, but good thing about this polynomial is in one polynomial you have all the solution of your radial wave function for hydrogen, radial wave function for hydrogen. So, Laguerre polynomial for n is equal to 1, L is equal to 0 will be given by this. Remember 2L plus 1 is equal to 1 and n plus L is equal to 1. Now, if n is equal to 2, L is equal to 0, then what you need is this polynomial, right, L12, because again 2 L plus 1 is equal to 1, but n plus L will be equal to 2. So, this is 2 L plus 1 is equal to 1, n plus L is equal to 2. So, this is your P and this is equal to Q, and the Laguerre polynomial for this is 2x minus 4, which I just showed you how to calculate. And again this we will get when n is equal to 2 and L is equal to 1. So, 2 L plus 1 is your 3 and n plus L is 3. Okay, so, this is P and this is Q, and you have Laguerre polynomial for this thing. Similarly, you can get Laguerre polynomial for n is equal to 3 and L is equal to 0. Here 2 L plus 1 is equal to 1 and n plus L is equal to 3. So, 3 1 x. This all I have solved. So, just by expressing solution in one polynomial, which is known as Laguerre polynomial, you get solution for each n and L, each n and L. It looks complicated, but it is important to understand these things. So, now we know what is the acceptable wave function and what is the wave function for different value of n and L. Now, we can discuss what is the energy, and in the last lecture I discussed about how to calculate energy. I showed you when L is equal to 0 and n is equal to 1, what will be the E n, and n is equal to 1 and L is equal to 0. Okay. I also showed you when L is equal to 0 and n is equal to 2, then what will be the solution. The solution is given by this H cross by 2 mu gamma square, and then I proved it that this is the way E n looks like. Okay. This is reduced mass Z square E 4 divided by 2 H cross square n square by 4 pi epsilon naught square. You see everything is constant except n. Okay. So, what does that mean is E n is proportional to 1 by n square for hydrogen atom. Certainly, if there are other kind of nucleus, then Z will also come into play. For hydrogen like atom, Mn is quite greater than Me, and so reduced mass is simply equal to Me. If you remember, mu is equal to M into M by M plus M, right. And since this M is or Mn, this is basically your Mn, this small m is your Me, and since this capital M is quite greater than a small m, so this will be equal to M into M. This is approximately equal. So, this is cancels out, this is approximately equal to mass of electron. So, what we will do is we replace mu by m, and then I have simply written this as Z square E square by 2 n square into 4 pi epsilon naught. What is left is your mu, which is equal to Me, then E has power 4. I have already written E square. So, there will be another E square, 4 pi epsilon naught square, one term I have written here. So, left is 4 pi epsilon naught into H cross square, and this is equal to 1 by A naught. This is equal to 1 by A naught, where A naught is called Bohr radius, which is basically derived when Bohr proposed his model for atoms. So, En is basically equal to minus Z square E square by 2 n square into 4 pi epsilon naught A naught, and A naught is your 52.9 picometer, which is the most probable distance from the nucleus to electron in the ground state. So, now let us again think of En. So, this is your En, that is we already discussed. This is simply mu E4 by 8 H square n square 1 by epsilon naught square. This is same thing which we got in previous slides. Now, think of a transition between electronic level in a hydrogen atom. So, suppose you are going from N1 to N2. So, what will be the frequency of the transition? So, frequency of the transition can be calculated by taking the difference between the energies of the two levels and divided by H. So, first we will calculate delta E, and what we will get is this one. So, this other things are constant except n, and so you see this comes in bracket, and this is your 1 by N2 square, since it is going to N2, and we started with N1. So, you write 1 by N1 square, and delta E is equal to H nu. So, divide by H. When you divide by H, then you will get H q, and frequency will be equal to this term, and this whole constant is equal to what is known as RH, which is Rydberg constant, and Rydberg constant has this value in your meter inverse. Okay. So, it is in meter inverse. So, please keep in mind this is in meter inverse, where frequency is in hertz. So, you need to convert this. So, this is basically wave number unit, and so you need to convert it into frequency unit. Okay. Then place here. So, frequency associated with the transition in hydrogen atom will be given by this equation. Okay. So, delta E is equal to this, and this whole thing, if you talk about in energy term, then this will be equal to 13.6 electron volt, and so delta E can be calculated using this equation. So, let us talk about what is known as gross spectrum of hydrogen atom. So, for hydrogen atom, delta n, our selection rule is delta n can be anything. Okay. We are talking about emission spectra. So, transition can be between n is equal to 2 to n is equal to 1. It can be from n is equal to 3 to n is equal to 1, and 4 to n is equal to 1. So, this is known as Lyman series. So, Lyman series corresponds to transition between your n is equal to higher value, any higher value to n is equal to 1, n is equal to 1. The second one is Balmer series, okay, Balmer series. It corresponds to transition between higher energy levels to n is equal to 2. Similarly, Paskin series, this corresponds to transition between n is equal to higher value to your n is equal to 3. Similarly, your bracket, again this corresponds to transition between your n is equal to infinity to n is equal to 4, n is equal to 7 to n is equal to 4, n is equal to 6 to n is equal to 4. So, any higher value, transition between any higher value of n to n is equal to 4. When I say any higher value of n here, what I mean is n is equal to greater than, or n2 should be greater than your n1, okay, n1. So, here n1 is equal to, or n2 is equal to, okay. So, let us see, this is n1 if, so n1 can be of any higher value, n2 will be always 1. So, in Lyman series n1 is greater than 1, n2 is equal to 1. In Balmer series n1 is higher than 2 and n2 is 2. In Paskin series n1 is higher than 3 and n2 is 3. So, similarly, you can talk about other series. So, this is your gross spectrum of hydrogen atom. Selection rule already talked to you, that selection rule governs the promotion of an electron to an excited orbital and also its falling back from the excited orbitals R. These are the two selection rule. For gross selection rule, we do not need the second one, but then I will talk about fine structure and we will see the what is the importance of the second selection rule. So, selection rule for electronic transition is that delta n is unrestricted, delta L is plus minus 1. So, this is your atomic spectra. So, you see n is equal to 1, this is 1 s 2 p. So, here you see this is your Lyman series. Okay. You can talk about emission, you can talk about absorption, both. So, here n is equal to 1 and here you can say n dash can be anything, which is greater than 1. Okay. In case of absorption, it is n is equal to 1 to n dash is equal to n greater than 1. Whereas, in emission you have the transition is happening from n greater than 1 to n is equal to 1. Now, you see this transition is also possible. Here you see what is changing is L value. So, here L is equal to 0, here L is equal to 1. This is for s electron, this is for p electron. So, delta L can be minus 1, delta L can be plus 1, delta L can be plus 1, while delta n can be anything. Okay, delta n can be anything. So, this is the way to show your gross atomic spectra of hydrogen atom, gross atomic spectra of hydrogen atom. But if you look at the hydrogen spectra, you go to more detail, then you will see that there is splitting of the orbitals, and corresponding to that you have a fine structure of hydrogen atom. The fine structure is just due to these two things, spin orbit interaction a relativistic kinetic energy correction. So, I will not discuss relativistic kinetic energy correction because that is more related to your exact value of energy, but I will talk about spin orbit interaction because that leads to splitting of the energy levels. Okay. So, let us discuss spin orbit interaction. So, first let us think of what kind of motion an electron undergo. So, an electron undergo rotational motion. Any rotating object possesses angular momentum. Any rotating object possesses angular momentum, and your electron is also making rotation. So, it must have angular momentum. The way angular momentum is given is this: J is equal to m into v into r. Okay. So, m is mass. So, suppose in this case it will be mass of electron, v is velocity, and r is distance from the center. And the direction you can also know. The direction is given by right hand rule, okay, by right hand rule. So, if you see this, if this is the way electron is rotating, then your angular momentum will be in the direction of thumb. So, you see here it is like this. So, it is coming out, okay. It will be up. If it is going from my way, this is anti-clockwise, then it is going up. If it is clockwise, then it will go down. Okay. So, the direction of angular momentum will be decided by the direction in which electron is rotating. Electron is rotating. Now, if an electron is moving in its orbital about a nucleus. So, electron is moving in its orbital about a nucleus, and so it will possess orbital angular momentum, which will be given by this formula. Okay. This we have already discussed in a rotational motion chapter, and that is given by L plus 1 half multiplied by h cross. So, h cross multiplied by square root of L plus 1, and this L star denotes L plus 1 half. Here L can take value from 0 to n minus 1. So, this is your orbital angular momentum, and that is because of electron is moving around nucleus in its orbital. Okay. So, these are the allowed direction of electronic angular momentum vector, which I discussed earlier. So, I am going to leave it. Suppose this is a nucleus and electron is moving around. Electron is at one position, it is also spinning, and that spinning gives the electron a spin angular momentum. So, electron also have spin angular momentum, since it is also going spinning, and that is given by s plus 1 half into h cross, or h cross multiplied by square root of s into s plus 1. Here s can take half only, and total angular momentum is basically sum of this two angular momentum, and it will be given by your this formula. So, j plus 1 half into h cross, where j can have L plus s to L minus s value. This we have already discussed in the rotational motion, but just to refresh you with this angular momentum, I just revised it. Okay. So, now sum of two vectors a and b tells you that if there is A and B, then this is your vector C, and this is another way to look at vector C. So, A plus B give you vector C. Now, let us think about, this is about angular momentum for any electron. Now, let us think about angular momentum for electron in hydrogen atom. So, suppose if I consider one s1 electron or two s1 electron. So, what will be the L? L value is 0 and S value is half, and if you calculate J value, it will be equal to plus half. So, only one value of J is allowed, and thus it will have one energy level. For two p1 electron, L is equal to 1 and S is equal to half. Okay, L is equal to 1, since p orbital corresponds to L is equal to 1 and S is equal to half. So, J can have two values, plus 3 by 2 and plus 1 by 2, and so you will have two energy levels. So, this is to know how many, or a particular energy level is split into how many energy levels if there is a coupling between your L and J, a spin orbit coupling. So, for 2p1 electron, there will be splitting into two energy levels, or 2p level is basically split into two energy levels, one corresponding to J is equal to 3 by 2, another corresponding to J is equal to half. Now, let us think about how to get the energy associated with these levels, energy associated with these levels, because you see 2p orbital is like this, and now we know that it is splits into 2. So, now question is, I know the energy of 2p level, it will depend on n, but I do not know the energy of these two levels, and unless we know the energy of these two levels, I cannot calculate what will be the delta E, what will be the delta E. So, now look at your fine spectrum of the hydrogen atom. So, first thing is to calculate the energy of these two levels which are initially degenerate, but they split because of a spin orbit coupling. Now, first we need to understand the magnetic moment. Electrons are charged, and so when they will rotate, they will also induce magnetic field. So, not only we are talking about your angular momentum, anything which is rotating will have angular momentum, but the things which is rotating has charge, then you expect a magnetic field to be induced, and the magnetic field is just opposite to, or what is called as magnetic moment direction will be opposite to your direction of angular momentum. So, for example, just I told you how to get the direction of angular momentum. So, you see electron is moving like this. So, if you do that right hand rule, and so you see this is going down, and that is what shown here. So, angular momentum direction is this, then magnetic moment direction will be this, and I will tell you how. But first let us calculate the magnetic moment. So, first thing is, since electrons are also charged, one would expect a magnetic field will be induced. Okay. So, let us calculate magnetic moment. Magnetic moment is given by this sign, and L shows you that it is because of the movement in a orbit. Movement is in a orbit, not due to spin, and this is equal to I into A, where I is current and A is area. This is the way magnetic moment is calculated. And what is I? I is dq by dt, change in charge with respect to time. And what is dt? Time is distance by velocity. So, this is your dx by c. So, I will be written as dq by t, dq by dx by c. And if I want to calculate I average, current average, then I will simply write C into delta q by delta x, C into delta q by delta x, and delta q is E, which is charge of the electron, by 2 pi r. So, this delta x is 2 pi r, which is perimeter of a circle. Okay, and A, we know A should be equal to pi r square. For this circle, area is pi r square, and so mu L, magnetic moment or orbital magnetic moment, will be equal to minus C E by 2 pi r into pi r square. And pi cancels out, 1 r cancels out. So, what I will get is minus E by 2 m and then m c r. So, what we did is I multiplied numerator by m and denominator by m. So, we have minus E into m c r divided by 2 m, and this m c r is equal to your j, or orbital angular moment L. You can say here L, let us write L. So, this is your angular orbital moment, angular orbital moment. So, magnetic moment and angular orbital moments are related, and they are related by this equation. Okay. So, this is your mu L is minus E by 2 m into L. So, there is another way to write this, mu L is minus mu B by H cross. This is called Bohr magneton. Okay. So, mu B is equal to, if you see that mu B is equal to your E H cross by 2 m, E H cross by 2 m. And so, E by 2 m can be written as E by 2 m will be mu B by H cross, and that is what I have done here. Okay. So, mu L can be written in terms of mu B. So, this is equal to minus mu B by H cross into L, and we know L is equal to H cross square root of L L plus 1, and this H cross cancels out. So, mu L is equal to minus mu B into square root of L L plus 1. This is your magnetic moment due to orbital movement or electron movement in orbit, electron movement in orbit. Okay. So, that is what we derived, mu L is minus E into L. So, let us write this L, this is L, this is the angular orbital moment, and this whole thing can be written as gyromagnetic ratio of electrons. So, magnetic moment can also be written in this term. Okay, this already we discussed how to write mu L in different notations. Okay. Mu j can also be written. In that case, L will be replaced by L z, and mu z can also be, and L z is equal to, we know that m h cross. So, here we have written in terms of m h cross, and mu z will be given by minus mu b m. So, this is about magnetic moment due to orbital magnetic moment. Similarly, we can write the spin moment, okay, same way, only thing now we are considering spinning of electron rather than its movement in orbital around the nucleus. So, spin moment can also be written like this. Now, let us think about spin orbital coupling, and I already told you how to know the direction of angular momentum and magnetic moment. So, you see this is your spin movement, spinning, and this is orbital movement, orbital rotation. Now, you see this is going anti-clockwise. So, apply right hand rule, then the direction of angular momentum will be up, okay, and so direction of magnetic moment will be down. Now, let us see why this direction is down, or just opposite to your orbital angular momentum. Now, this is your equation, am I right? If you go, this is your equation, you see there is a minus sign. Okay. So, what will be the direction of L? The direction of magnetic moment will be opposite to it, and that is what is shown here. Now, you look to the spinning of the electron, and that is also in same direction, and so mu s is going to be in the same direction, and so J is equal to L plus S. Now, take the opposite case, electron is moving in the orbital in anti-clockwise fashion, where spinning is in clockwise direction. In that case, mu L will be down and the direction of mu s will be up, and so your J will be L minus S, and that is why splitting. Now, let us go and calculate what will be the energy. So, let us see, there is your, here is your electron moving and this is your nucleus. Now, what I am doing is that I take a reference where electron is static, center of mass is moving. From the Ampere's law, we know that if this happens, that will result into a magnetic field, and that magnetic field will be given by B. So, B is equal to mu naught, where this mu naught is your permittivity, okay, permittivity of the medium, into I is current, divided by 2 R. R is this radius or distance between nucleus and electron. So, this is from the Ampere's law. Okay. I just we calculated what is, so let us see what is the I. So, if I go here, here you see current is equal to mu L by A, and mu L is this, am I right. So, I will be mu L by A, and mu L is, so I is equal to mu L is minus E by 2 m A into L. So, remember this, minus E by 2 m A into L. Now, go and see here. Okay. I is equal to, let me write, this is mu L. Okay. So, please change this. So, mu 0 mu L by A. So, I showed you that your mu L is equal to I into A. Let us write I, mu I is equal to mu L by A. So, B is equal to 2 R into pi R square. So, 2 pi R cube. So, this is your 2 pi R cube, and Z I introduced because here your electron not only have charge E, it is Z into E, that is why I introduced Z. Okay. So, this is your B, mu naught Z mu L by 2 pi R cube, and if you remember mu L, it is E by 2 m L. So, you have this expression. So, mu naught by 2 pi R cube Z D by 2 m into L, and for average field you just take 1 by R cube out, and you have to take the average of 1 by R cube. So, this is your magnetic field due to your orbital motion. Now, Let us think about spin orbit coupling. So, how to write the Hamiltonian for spin orbital coupling, and for that you have to calculate this Hamiltonian will be given by mu s. So, this is, remember, this is due to spin, magnetic moment due to spin into B, and this already we calculated. B we already calculated, this is mu naught Z d by 4 pi m 1 by r q l and into mu s, and mu s we have expressed this by this term, and you have this quantity, and now you, if you simplify, you take s this side, then you have L into s and all constants, L into s into all constants. So, this is your Hamiltonian for a spin orbital coupling. This is Hamiltonian for a spin orbital coupling. Okay. Now, let us calculate L into s. We know that J is equal to L plus s. So, J square will be L plus s into L plus s. It will give you L dot L plus s dot s plus 2 dot L dot s. So, L dot s will be half of your J square, which is J into J minus. So, let us take this side, this 2. So, L s is equal to J square minus L dot L minus s dot s divided by 2, that is what it is written here. Okay. So, L dot s is equal to h cross square by 2 j j plus 1 minus L L plus 1 minus s s plus 1. We know that j is equal to h cross j j plus 1. So, j square will be h cross square j j plus 1, that is what is written here. So, now we have calculated L dot s. So, we can now calculate delta E. So, effect of spin orbit coupling on hydrogen fine structure. Okay. So, when there is coupling, then you get a fine structure. So, delta E S O is given by A by 2, A is a constant, and j j plus 1 minus L L plus 1 minus S S plus 1, and A is equal to this whole value, which is basically given here. If you remember, this whole value is your A, and so this you can say this is some constant A into L into S. Okay. So, that is what. So, A divided by 2 and then this. So, A is basically the constant there. So, basically this constant is, if you look at this constant is A by h cut square, and if I multiply by, so A by h cross square into h cross square by 2. So, this is A by 2, that is what we got here. A by 2 j j plus 1 minus L L plus 1 minus S S plus 1, and A will be here. And now you can calculate what will be the delta E for 2p1 electron. So, for 2p1 electron, J can be equal to 3 by 2 or half, that is what we saw. And when J is equal to 3 by 2, then if you calculate j j plus 1 minus L L plus 1 minus S S plus 1, you will do this calculation, and then what you will get is plus 2A. So, 3 by 2 plus 1 minus 1, since L is equal to 1. So, here 2p1 means L is equal to 1 and S is equal to half. So, this is going to be same, only thing is that J is changing, and J is basically 3 by 2 or half, and that is why you get two values of delta ESO. So, plus 2A and minus A, and so now you know the effect of spin orbit coupling on 2p1 electron. So, 2p1 will be split into 2 energy levels. This will have, if you have j is equal to 3 by 2, then it will have energy. So, you see here plus 2a, this is wrong, this will be plus 2a and this will be minus a. So, this is your energy level. Now, how to denote these energy levels? So, just we saw that if an electron is in 2p level, then it will be split into, the energy level will be split into 2. Now, question is how to label it. The generally we label it is the rule which follow is for labeling is 2s plus 1 Lj. So, if L is equal to 0 means you give value s, if L is equal to 1 give value p, L is equal to 2 then you label it by d, if L is equal to 3 label it by f. Okay, selection rule I already told you, so I am not going to discuss. Only thing you need to know is that delta n can be anything and delta L should be plus minus 1. So, what does that mean is the transition is allowed between 1 S1 to 2 P1, 1 S1 to 3 P1 also, because delta n there is no condition, and then you can have 2 S1 to 3 P1, okay, 2 S1 to 3 P1. So, all these kind of transitions are allowed. Now, let us see if we have electron in 1s or 3s level. So, for s electrons L is equal to 0, s is equal to half, and so j will be half. There is only one value of j, and since L is equal to 0, so it will corresponds to, it will be given label s, and 2 s plus 1 is equal to 2 into half 1 plus 1 is equal to 2. So, there is a 2 here, and j is equal to plus half, so 2 s half. So, there is only one label which will be labeled as 2 s half. If you have electrons in 2p level, then L is equal to 1, s is equal to half, or any p level you have L is equal to 1 and s is equal to half, then j will have two different values, plus 3 by 2 and plus half, and since L is equal to 1, that corresponds to label p, and 2 s plus 1 will be 2 plus 2 s plus 1 will be again 2, and j has two values. So, you have a two energy levels. So, one energy level is labeled as 2 p 3 by 2, another energy level will be given by 2 p half. Notation for energy level associated with 3d1 or 4d1 electron means we are talking about d electron. For d, L is equal to 2, and if you have 1 electron, then s is equal to half, and your j value will be plus 5 by 2, 3 by 2. L is equal to 2 corresponds to level d, and then you have these two energy levels, or labeling of two energy levels will be 2d 5 by 2, 2d 3 by 2. Since j has two values, it means that the energy level will be split into two different energy levels. 3d energy level will be split into two energy levels. What will the name? Name will be 2d 5 by 2 and 2d 3 by 2. So, now look at the spectral line of hydrogen atom. Here we are discussing about hydrogen fine structure. It will be composed of closely spaced doublet. For example, if you are going from 3s to 2p, I told you 3s there will be no splitting, for 2p there will be two energy levels. Because of a spin orbit coupling, 2p level will not be degenerate, it will be split into two different levels given by j is equal to 3 by 2, j is equal to half. And that corresponds to two different lines in the hydrogen spectrum. In totality, what you will see that you have, suppose this is 2s, this is 1s, your 2p is split into 2, 3p is split into 2, 4p is split into 2. Similarly, 3d is split into 2, 4d also is split into 2. The splitting, the gap between the split energy level will be higher for 2p, lower for 3p and much lower for 4p. If you go this side, the splitting will be smaller for 3d in comparison to 3p or 2p, but if you go up, the gap between 4d will be smaller in comparison to gap between 3d. And this all transition are possible, 1s to 2p, 1s to 3p, that is what we talked. We cannot go from 1s to 3d, because then delta L will be plus 2, that is not allowed, but delta L is plus 2, which is not allowed. Delta L is plus minus 1 is allowed. So, it can go from 2p to 3s, 2p to 3s, but this is your finer or fine spectrum of the hydrogen kind of atoms. So, now you see this is what we are showing is compound doublet spectrum arising as a result of transition between 2p, 2d levels in hydrogen. So, before that I discussed transition from S to p level. Now, I am seeing the transition between p level and d level. Now, you see here 2p 3 by 2 to 2d 3 by 2, 2p 3 by 2 to 2d 5 by 2, that is possible, and 2p half to 2d 3 by 2 and 2p half to 2d 5 by 2, and so there will be doublet here, there will be doublet here. So, this is your transition between 2p and 2d level, which will result into double doublet. So, this is the way to understand the fine structure of hydrogen atom. So, today I discussed the fine structure of hydrogen atom. I am not going to discuss your relativistic effect, because it is a bit higher in thinking and it is not required for this course, but I hope that you are able to understand how the splitting takes place when spin orbit coupling happens, So, thank you very much for listening. These are the different books which I am taking notes from. So, Alberti, book from Alberti, book from Peter Atkins, and then Fundamental of Molecular Spectroscopy from Banwell and McCash. Thank you very much.